So in paper 2, we have studied linked list. So basically we do understand its overall working. We haven't yet looked at the algorithm. Now we'll be looking at the algorithm as well. And if you remember what happened in paper 2, basically, as mentioned before, may it be a linked list, may it be a hash table, may it be a binary tree, underlying concept is that they're all arrays, right? So yes, they are arrays of different data types. For example, this linked list will be an array of type node. And as you remember, node is a record data type that we create, is user defined data type that we will create to hold two data items. And binary tree is a similar concept, but it has additional information that will be discussed in another lecture. Now, first of all, let's just go through the basics of what a linked list are. Just a quick recap on this. So basically, a linked list is, as mentioned, it's a list. And the reason that it's called the linked list is because each aspect of a list basically is linked to another aspect of the list. So the term aspect I'm using here, that one thing that each individual part of a list, that is known as a node. So basically these nodes are interconnected together to form what is known as a linked list. Now, what a node is, basically, it is a record data type. You will be creating this in your algorithm. It's a record data type that is meant to hold two data items. One will be the obvious data that it's supposed to hold. That's the value that it's supposed to hold. So this, for example, you see linked list over here. These individual nodes that we see that have the letter B and say D and the L in between, that's your individual data items that you're supposed to be holding in each node. And the second data item that each node will have is the pointer. Now, pointer basically is an integer type field of a record, and it is supposed to hold, again, the index positions of the next node. Now, the reason I'm emphasizing on index position is because regardless of whatever technicality you see in front of you, linked list is inherently just an array. So as mentioned before, as we've discussed in paper 2, we've always discussed regarding arrays, each position in an array is identified separately based on this index position. Same thing applies here. If it's an array of nodes, which it is, each node, the position of each node is identified by its index position. So if, say, for example, I'm at this node, this index position, this pointer will point towards the next node that comes after this node. Now, it's interesting that why do I need a pointer to tell me which node comes next when everything can be in contiguous locations, index position 1, 2, 3, and so on and so forth. Well, that's the beauty of a linked list. It is an array underlying, but it defies the basic, limitations of an array. By that, it means that if you have an array and a conventional array, a conventional array does not allow elements, data items to be added in between somewhere. So if it's a Python list, for example, then you can add elements, you can append it to the end. But conventional arrays do not allow elements to be either deleted or added in between. There are techniques in which you can copy the elements of an array and add a new element in between and create a new array. But that doesn't mean that you're changing the existing array. You're basically creating a new array with the new properties, so on and so forth. So a linked list, on the other hand, it allows these kind of operations. So if you have if you have an array of nodes, you are perfectly within your rights, within your capabilities to add a node or an element in between anywhere. You can add it at the start, you can add it at the middle, at the end, wherever you want. Similarly, you're also allowed to delete elements from the array from wherever you want. So if you want to delete a node from between, you can do that. You want to delete it from the end, from the start, you are completely allowed to do that. Now, the reason that you're allowed to do that is these nodes are not connected in, say, numerical order. That order is really, it doesn't mean anything, because each node, when you reach the first node, and again, the first node can have any index position, but it's first because of the ascending order of the data values inside it. Now imagine that this linked list you can see here starts with B, then D and L. Apparently it's in alphabetical order. Now that doesn't necessarily mean that B was the first node to be created. It is quite possible that B was the second node to be created or the third node to be created. So by that logic, B should have come at the end. But that's not the case here. B as at the start. Even if B came afterwards, but since linked list allows me to add a node wherever I feel right, I can add B at the very start. So this is the beauty of linked list. You can add nodes and delete nodes wherever you want to do it. And this is something that your conventional array is not allowed to do. So this is the underlying concept of your linked list. The why of the linked list. Why do we need a linked list? Is because we want to have a little more flexibility with moving around data. And order is not significant because when I arrive at a node, I will just have to look at the pointer to know where to go next. And so the pointer is telling me from here, the next node that is available to you is here, the next node is here, and so on and so forth. Okay. Now, as you can see here, we have two different lists. Now, again, as always mentioned, this diagram that you see in front of you, this is just a logical representation. What that means is that it's just for you to understand. In reality, the computer does not have to store data in this way. It's stored, of course, in their machine code in a separate way, in a completely different version. But for you, this diagram is there created for your understanding. Now, according to this diagram, I can see two lists. Again, this division of this list, these two lists are basically the same list, but they're logically divided into two lists. One part is the actual linked list. Now, what is the actual linked list? These are the nodes that are connected together and they're used nodes. They have data inside them. So all of the nodes that are combined together that are used, that's your actual linked list. That comprises of your actual linked list. On the other hand, you can see this other list, that is the free list. The free list comprises of all nodes that are not yet used. So these are the nodes that are not used yet. So the start node, the start of your used linked list or your actual linked list, that's represented by this variable here over here. So basically the start pointer tells you what's the first node. And once you reach the first node, every node has a pointer value pointing towards the next node. So all you have to do is just move to the first node and each node will basically tell you itself where to go from here. And if you see this thing, this symbol represents null here. So null means nothing. So if you have a null pointer, it means that this node is pointing towards nothing, in which case it means that there is no node after this one. So if you ever encounter a null pointer, that means you have reached the end of the list. Okay. So as you can see here, both start pointer and your free list pointer both have null at the last node, and that basically means that there is no node after this. Okay. So we have two variables here, start pointer, free list pointer. Start pointer is pointing towards the first node in your actual used linked list. If start pointer has a value null in it, that means that your linked list is empty. None of the nodes have been used. On the other hand, if your free list pointer has null in it, that means there are no more free pointers available and your exact array of nodes has been completely filled. So moving on, the different operations that are allowed in your linked list resemble something like this. So for example, if I want to add a node at the start, now as you can see here, my original linked list had BDL. Now let's just say, this is node index position 1, index position 2, and index position 3. Coincidentally, the index positions are in order. Now I have a fourth index position node, a new node, in which the value A is to be entered, like this one. Now, technically, it's the fourth node. It should belong at the end. But since it has a value which is lesser than all other values in it, so we are allowed to put it at the start and thereby maintaining the ascending order of values. How do I do that? Well, quite simply, first of all, I will copy the existing value held by the start pointer and I will assign it to the new pointer's pointer position. So basically what that means is that this new node is now the start pointer and this existing start node is now the second node. So basically this new node that I just added will, since it's at the start, will actually be pointing to the existing, the previous start node. Okay. So the first step you will be taking is, again, I repeat, the first step you will be taking is that you will take the start pointer contents and place them in the pointer contents of this new node. Why is that important? Because, of course, If we remember the working of a variable, as soon as I assign something to a variable, the previous value is overwritten. So if I were to update the start pointer to point towards this node as a start, that means as soon as I assign the index position 4 to this value, this variable, the existing value will be overwritten. So I have to save that somewhere. How do I save that? First, I copy this value and save it in this pointer position. So now a link between this node and this node has been established. Second thing I need to do is I have to establish that now this new node, since it has the value A, which is the least value, it belongs at the start of the list, in which case I will assign this index position 4 in this start pointer. So now technically my start pointer is pointing towards this node as this first node, and every node comes after this, so on and so forth. Similarly, if I want to add a node at the end of my linked list, I can do that very easily. So let's just say I added a new node, and as you can see here, based on my existing data, this data should belong at the end. So that's why this node is supposed to be added, connected to the end. So now previous last node was L, and the pointer value of that node was null. So that meant that after L, there's no more nodes, and that's the end. That's the end of it. Now, since I'm adding a new node to it, say this is again index position 4, 1, or call it 5. It doesn't matter. So let's just say this is fifth node right here. This is fifth index position of my array of nodes. This is my fifth index position node. And according to this data should be at the end. So what I do is that I will first of all remove this pointer position, and it should no longer have null in it. Because this node is the last node, it should have null in it. So instead of having null here, I assign this with null. Secondly, this node, which is index position 5, should be assigned here, so that this node, when I reach this node, I look at the pointer and I say, oh, there's another node at the end of this, and I reach here. So this is how we add a new node at the end. Similarly, if you want to delete a node from the start, it will look something like this. And now existing node, this with contents B was the start node. And let's just say that this node, index position 1, had 2 in its pointer pointing towards this node. And my start pointer had index position 1 in it, because previously, this node was at my start of the linked list. Now, what we do is that we simply copy the value of this pointer to the start pointer, so that this start pointer will point towards this node as the next available node. And this is how I have ignored this list node as my start node, and I will simply move directly at this node. Again, I have to make sure that this node goes back to the free list. We will look at how that's done in the algorithm, but for the time being, we should be clear that if I want to delete the deletion process, I'm removing this node altogether. It's very simple. What we simply do is copy the contents of this pointer to the start pointer. So that start pointer is now telling you that now this node is the start. No longer this node is part of the list. Same thing goes if I want to delete a node from the end of my linked list. Quite simply, go to the previous node, the second last node, and in the pointer position, write null there, so that it seems that this node, now it's the last one because it's no longer pointing towards anything. And again, I will have to do an additional few steps to make sure that this node goes back to the free list, so that now next, if I want to add a new element to my linked list, I have nodes available. These nodes are being reused. Finally, if I want to add anything in between, or in fact, if I want to add anything in between, so I'm adding this new node in between. So imagine that this is index position 1, 2, 3, and let's just say this is index position 6. Now this node number 6, it can be seen by the value that it belongs between B and node D. Even though it is a node with index position 6, but still my linked list will allow me to add this node in between because of its value. How that's possible is simple, that I will take the pointer position value of this node, copy it on this new node, so that this node starts pointing towards this node as the next node available after this one. And this node, which is node number 6, index position 6, will be assigned here. Now, if I do it the other way around, I will assign this value first and copy it next later. Both this pointer and this pointer will end up with the same value. So we have to be very careful with this, that first I want to save this value. And how do I do that? First copy this to the pointer position of this new node and assign the index position of this node to the pointer position of this node. And this how I will move from here to here. Finally, what I do here in the last option is I want to delete a node from in between somewhere. This was adding a node in between. I'm deleting a node in between. So again, quite simply, what I will do is I will take the pointer value of this node that I'm trying to delete and copy it to this node over here. And as you have guessed, this node's pointer position will be overwritten, and that's okay because it should not be pointing towards this node anymore. I just deleted it. So what we do is we simply copy the pointer position, the number, the contents of this pointer position of this node, and save them in here so that this node is directly pointing towards this node and ignoring this node altogether. Another way to represent a linked list is using these two-dimensional arrays. Now, the way that these two-dimensional array is organized is that the rows represent each node. So this is node with index position 1. This is node with index position 2, 3, 4, 5, 6, and 7. And the two columns for each row represent, the first column represents the data value. The second column represents the pointer value. Now, as it can be seen in this diagram over here, that node number 1, you see these square brackets, they represent index position. So node at index position 1 is pointing towards node index position 2, and node index position 2 is pointing towards 3, 3 is pointing towards 4, 4 is pointing towards 5, 5 is pointing towards 6, 6 to 7, as 7 is the last node, is pointing towards nothing. Now, as you can see here, that there are no data items in this linked list so far. Why? Because this is an empty list. These nodes are all free. So basically, this is my free list. And as you can see, the start pointer and free list pointer variables we see here, the start pointer has null in it, which means that there are currently no nodes in my linked list. By saying no nodes in the linked list, I mean that there are actually no nodes being used right now. All of them are free. And which is my next available free node? Obviously, it will be my first node. So that's why the free list pointer has 1 in it. So next in my algorithm, the next node that I will be using for data storage will be figured out by the contents of free list pointer. And the free list pointer is telling me go to index position 1. That node is currently free for you to use. Okay. So in this case, if free list pointer has null in it, that means there are no more nodes available for data storage. So this is what a free list looks like in two-dimensional version. On the other hand, if we have a partially filled node, and as you can see here, as mentioned before, a partially filled linked list means that I basically have divided the existing array of nodes into two parts. One part is the actual linked list with the contents filled of each node, and the other part is the free list in which each node is empty. So that's what's happening here, that this is my complete array of nodes, and the linked list ends here, and my free list starts from here. So that's why, as you can see here, node number 1, 2, and 3 have been used. So it's partially filled, but linked list ends at node number 3. And that's why after node 3, the next pointer is null because there are no more used nodes. On the other hand, as you can see here, my free list pointer is telling me the next available node for you to use is at index position 4 because my actual linked list has ended at index position 3. Similarly, since my list has elements in it, my linked list has elements in it, then that's why my start pointer is not having null in it. It's actually telling you that first node that is on your on your linked list is node number 1 here, which is B. And once I reach this node, the pointer will tell me where to go from here on each subsequent node. And if a pointer has null in it, that's where I stop. So far, we've just revised what we discussed in paper 2 regarding linked list. So basically we've had a logical overview of what the linked list, how it works. Now let's take a look at the algorithms involved in the different features supported by linked lists. In the first phase, we will look at how a new linked list with all nodes empty looks like, right? How that algorithm performs and what are the steps involved. In your examination, there have been questions in past papers that are basically, partially filled algorithms, and there are fill in the blanks, and you have to complete the blanks based on your knowledge about the working of these algorithms. Pretty interesting stuff, and it's actually pretty easy to understand once you get a grip on what this algorithm is, and you can just figure out what step is to come next, and you can fill in the blanks according to the variables being used for that particular question. So it's very important to understand the steps being carried out for each feature of the algorithm, feature of the linked list. So first feature or first module of linked list involves creating a new list from scratch. So right now there is no array of nodes. We have to create an array of nodes. So before we create an array of nodes, we have to create something that is it's known as a node. So this is where we declare our user defined type of type list node. And each node should have two fields in it. One is the data field of type string. These are the letters you see, A, B, C, so on and so forth. And one is the pointer field of type integer, which is basically telling me which node comes after this node. So basically each node has these two fields in it. And that's all we need to do about the list node type. Okay. One thing interesting here is that we are defining a constant by the name of null pointer. Obviously, I cannot use these symbols in any programming or algorithm design. So we have to come up with integer type values for each, for the null value itself. So the rule of thumb is that if you are using zero index, then if zero index is part of your array, then in that case, your null will be represented by -1. So that null is basically not part of your range of elements, index positions, and -1 should be null. However, if you're using index position 1 as the first index position in your linked list, in that case, 0 should be used as your null pointer, because in your acceptable range of index positions, 0 is not part of it. So we have to choose according to the state of our first index position. Now, according to the algorithm, our index position in the arrays ranges from 1 to 7. In this case, my first index position will be 1. So by that logic, my null should be equal to 0. So that's why we'll be choosing 0 for this. That's why 0 has been selected as null pointer. So we're done with the null pointer. We're done with declaring our type list node. This is the syntax for setting up type and untype. This is again concepts discussed in great detail in paper 2. Okay, we need a variable to hold the information, the index position of the first node. That variable should be called start pointer, and it will be of type integer. We will need a variable to hold the node number, the index position of the first available free node when we want to add more data. And again, free list pointer will be represented, will be used to represent that variable. And again, this will also be of type integer. I need an array. Like I said before, that may be a linked list or binary tree or a hash table. They are just basically arrays underlying. So again, we need an array of the name of array will be list. The lower limit of the index position will start from 1, and the upper limit will end at 7. So basically this array is of size 7, index position 1 to 7, and the type for this array is list node. So this array will be of type list. So basically each index position of list array will actually be a list node with 2 items, data and pointer, not an integer, not a string, not a boolean type. It will be of list node. Okay. So basically each index position of list will hold a list node. Okay. Now, how do we initialize? How would this procedure is for initializing? Now, basically, in simple terms, initializing a linked list means to bring it to this state in which there is no data, but I'm just creating that free list with all the nodes, and each node is connected to the next available free node, and last node should be connected with will have null in it, so on and so forth. So anyway, the procedure for doing that is, first of all, I assign my start pointer as null pointer because there is no data, there are no used nodes currently. So as mentioned before, if my linked list is empty, start pointer should have null in it. So that's why null pointer is being assigned to the start pointer. Secondly, my next available node should be one, as mentioned over here. So that's why one is being assigned to free list pointer. After this, I need a loop to run from 1 to 6, 6 times only, in which this is my counter index, for which in index position 1, the pointer of index position 1, pointer of the node in index position 1, in the array of list. So in list array index position 1, the field pointer should be assigned a value which is index position index plus 1. So basically, if my index is 1, I'm at the first index position of my list. The pointer field of that node will have index plus 1, that is 2. So as you can see here, my index first node at index position 1 node has index plus 1, 2 in the pointer field. And that's what we're doing here. And when the counter is incremented, this becomes 2. List index position 2 in the pointer field, I'm assigning 3, 2 plus 1. For the third node in the pointer field, I'm assigning 4. So fifth node, I'm assigning 6, and sixth node, I'm assigning 7. Now there were 7 nodes, and I'm ending this loop at 6. So that means the 7th node is not actually part of this loop. Now, why is that so? Because I have to give the 7th node a special treatment. And what that special treatment means is that basically the last node should not have plus 1 in the pointer. Because if you keep this loop to run to 7 times, that would mean for the 7th node, I will assign 8 to it. And there is no 8th node in your array. Your node ends up at 7th node. So technically, it should stop at 6 because the 7th node is to be treated differently. For the 7th node of my list array, I will assign null to my pointer so that it represents the last node that is available. Okay. So in these few steps, we have basically created a linked list with this status: start pointer as null, free list pointer as 1, all nodes connected through pointer and having no data in them. And there are 7 nodes. Now let's look at another feature of linked lists that can be included in your overall working of a linked list. Now this is how this procedure deals with inserting a new node into your existing linked list. So basically what that means is that I'm taking a node from my free list, I'm adding some data to it, and based on the value that data value, I am allowed to add that node wherever it is suitable based on the ascending order of the existing linked list. So it's kind of like this. If I want to add, say, node C, it belongs in between here. So I will do that. Now this node will be placed wherever it suits the order of the data values in each node. So the value that I'm entering will be passed as a parameter to this procedure insert node. So basically what the letter the letter I'm trying to add, B, C, D, whatever it is, that will be stored in this variable, this parameter value. Okay. So in the start of the procedure, I'm asking this question: if free list pointer is not equal to null pointer. Now, if this condition is true, only then this code will run. Only then. What that means is that if my free list pointer is not equal to null pointer, so that means if it actually, now think about it, if free list pointer is actually equal to null pointer, that means there is no room left in your linked list. So this code will not run. You won't be able to add this new item. This code will only run if this is not equal to null pointer. and my free list pointer is actually pointing towards a non-null value, telling you that there is yet at least one node available for you to add this new data item. And if this condition is false, and free list pointer is in fact equal to null pointer, this code will not run, meaning that new item may not be added. Now, if this condition is true and I have space in my array of nodes, only then this code will run. Now, the node in which I will be accommodating this new item will be referred, the index position of that node will be referred to as new node point. By the way, who told me which new node will be used, which node will be the new node? Obviously, I have to ask the free list pointer which node is available for me to use. So that's why the contents of my free list pointer will be saved into this node over here. So this is why you're assigning the contents, they're copying the contents of free list pointer into new node pointer. So now basically from here onwards, this will be the node that I'm adding this item to. Okay, so this is my next available node. Okay, so what we do here is that now since I am told by the free list pointer that next available node is this one, right away what I do is I will go at my array, I will go in my list, I will go to this index position, this new node that I'm going to be using, and simply assign this new item which I just passed as a parameter in its data field. Similarly, I have to also update my existing free list pointer. Why do I need to update it? So that next time around when I want to add a new data item, I will be told the next available free node that is available. So I have to update the free list pointer each and every time a new data item is added. How do I update it? Obviously, the node that I just used as my new item, the pointer position of that node is actually pointing to the next available free node. Now, if you remember here, let's just say that I just used this node for storing a new data item. And this free list pointer told me that this node is available for data storage. Now, as we mentioned in the algorithm, this free list pointer will now call this node as the new node pointer. So what is the new node pointer? New node pointer is node number 1. Okay. And which will be the next available free node? Obviously node number 2. How did I come about this information? Well, the existing new node that I just used, the pointer position is pointing towards the next available free node. So simply what I will do is that I will copy the pointer value of this currently node that I'm using and assign it to my free list pointer and update, and basically the updates to tell you that next available node will be node number 2. Now, there are 2 ways to do this and they will both end up doing the same thing. So as you can see here, if I, instead of using free list pointer here, I use new node pointer, it will have the same effect, because basically right now, my free list pointer and my new node pointer are pointing towards the same index position. So right now, this is my free list pointer and this is also my new node pointer. So if I take the pointer value and assign it to my free list pointer, now it's updated. But before this line, both my new node pointer and my free list pointer are both pointing towards the same index position. So it doesn't matter if you use free list pointer here. It doesn't matter if you use new node pointer here, makes no difference. You can use either one. So we've used free list pointer. So existing free list pointer, existing free node, the pointer position of that existing free node will tell you that this is the next free node is this one. So what we do is we take that pointer and assign it to the next free point, to the free list pointer to point towards the next available free node. So as far as assigning data to a new node, these are the only steps that we need to take place. If there is room in my linked list, I will simply refer to the free list pointer. Free list pointer will guide me to the next available free node and I will call that as my new node. Then I will take that new node the new node, and it's in data field, and I will assign the new item in its data field. Second thing, I'll have to update my free list pointer to point towards the next available free pointer. In which case, I will go to either the free list pointer or new node pointer index position, take the pointer of that node and copy that value to the free list pointer. So basically my existing nodes pointer is pointing towards the next available free node. And I simply made that transaction possible. I copy the contents of this pointer into this existing free list pointer. So by that logic, if currently the new node I just occupied, let's just say that it was currently the last node available. It's the last node available. There are no more nodes available after this. So in that case, when this line takes place, free list pointer will have null in this after this line, because the last available node's pointer position has pointer field has null in it. And that null will be saved here. And next time around, if I'm trying to add a new item, this condition will not make it possible. So this is how, as you can see, the algorithm is designed in such a way that all pointer positions are automatically updated and updated for the next round of events in which I'm adding a new item. Now, as you can see that we have taken a node, we have assigned our data item in the data field of that node. We have updated the free list pointer to point towards the next available free node. We've done that. Now we have this node that's technically not actually yet part of my linked list. Okay, so the next step, we will be finding an insertion point in my linked list. Now, again, as you remember, the working of my linked list allows a node to be added anywhere amongst my existing linked list. I can add it anywhere, between, start, wherever, at the end, wherever it is. So, and the decision making process that helps me decide where this node is to be added is based on the value, the contents of its data field. So as you can see in this example, C belongs between B and D, and that's where it's going to go. So this is the insertion, but the algorithm will decide that C should be here based on the contents of the node. So that's exactly what we're doing over here. So we have this node, it has the value in it, but it's not yet part of the list. Now I have to find a place where this node should be added to my linked list. Now it could be added in the start. It could be added. It could be the largest possible value that is yet has been added to my linked list, in which case this new node will be ending up at the end. Or it could also be the smallest value to be entered till now, and it will be added at the start. Or it could be in between somewhere like so. It will be added in the middle. So this decision will be made, and this is the steps involved in that decision. So for example, how I'm gonna find out which node should be, which position my new node should be added at. Quite simply, I will start at my first node, look at its contents. If the contents of this node are lesser than my new item, then obviously I will move ahead. If the next node contents are also lesser than my new item, I will move ahead. Next node to the next node right here, the next node. If the next node are now larger than my new item, then I will stop right here and I will add this new node between this larger node and the previous smaller node. So in this case, say I was trying to add C to it. I started at the absolute beginning of my linked list. The contents of that node is smaller than my C node, this node with C data in it. So obviously I won't store here. I will move ahead of this because we're maintaining ascending order. I'll move on to the next node, D. Now D's value is no longer lesser than my new item, in which case I cannot go beyond this. I obviously have to store it behind this. And since I moved ahead, so I have to store it ahead of this, behind this, so in middle here somewhere. So this is the decision. Obviously, if at one point I moved on and maybe I had to save it before this, so like in this case, I want to save C before D. So obviously if I have moved on to D, and for pointers to be updated, I need to know where I came from and where I'm going. So that's why at each step of moving from one node to the next, I have to keep record of what node I just left. So what that means is that if if I'm trying to search for an insertion point, I did not find a position here. I moved on to the next node. If I did not find an insertion point here, I moved on to the next node. And as I move from this node to the next node, the previous node will also, the record of the previous node will also be saved. Why the record of the previous node is needed? Well, obviously, if I stopped here, my new node will be between this node and the previous node. So if I don't remember what the previous node is, how will I be able to add this node in between? So that's why each time I move from this node to the next, I keep record of the previous node so that if the next node is larger than my current value, I add it between my previous and this node. And I can only do that if I have previous node saved. So that's exactly what's happening in this algorithm. So I start from searching from an insertion point at the start of my linked list. What better variable to hold information of the start of my linked list other than my start pointer? So that's why I will ask the start pointer, okay, start pointer, where should I start searching for my linked list? Start pointer says index position. This is my first available node, first used node. So start here. I will take that contents. I will take that node number and I will call it, okay, right now I'm looking at this node right now. What are the contents of this node right now? So each time I'm evaluating the contents of that node, I'm looking at the contents of this node right now. So each time I move on, that will be my this node. Then I move on, that will be my this node. But my first this node will be told to me by the start pointer. So that's why I'm copying the contents of my start pointer to this node point, and I will start searching from here. Okay. We have this loop here. The loop says as long as this node pointer is not equal to null pointer and the contents of this node pointer, the node I'm looking at right now, the data of this node right now, the node that I'm looking at is lesser than the item that I'm trying to enter, I will have to move on. So let's just say, for example, I have not reached this node is not equal to null, for example, and the contents that I'm trying to add are, say, M. I'm trying to add M. So I start at this node. This node is told to me by the start pointer. Start pointer says node number 1 is your first node. Okay. Is this node equal to null? No, it's not. It's equal to 1 right now. Okay, that's good. Is the contents of this node lesser than my new item, which is M? Is it? Yes. If that's true, then I have to move on to the next node. Now, how I'm moving on to the next node, before I move on to the next node, this status of this node will become previous because I'm moving on. So first, what I do is I will save the contents of this node into another variable known as previous node. And how do I shift to the next available node? Very simple. The contents of this node right now are telling me the next available node is this one. So how do I simply move on? First, I did that. I will call this node as my previous node. I will copy the contents of this node into a variable previous node. And I will copy the contents of the pointer field of this node and save them into my variable this node. So basically, if this is my first node, node number 1, the contents of this node are, this is node number 2, by the way. So the contents of this node is node number 2. So this node number 1 is now my previous node, and the contents of this node, which is 2, will now become my next this node. So now I'm focusing on this. This is my previous node. This is my this node. I'm trying to add M to it. So according to this logic, my M is greater than this as well. So again, move on. This time around, this will become my previous node, and this will become my this node. So I moved on. So the contents of this node are still lesser than my M. Remember that each iteration of my while loop, I'm also checking whether or not this node pointer has become null. So far, it has not become null. So as you can see in this node, my contents are lesser than M. So that means I have to move further ahead. So How do I move ahead? This becomes my previous, and my next available node will be referred to by the pointer of this node. So basically, the contents of this node from this line onwards will become null. So now my while loop condition will fail, because while loop condition is checking whether or not my this node has become null, in which case it has. So the condition that this node is not equal to null will have failed, and I will exit the loop. In which case, I will have to add this new node with letter M in it at the end. So that's exactly what's happening here. I will start at the very beginning, and the node that I'm evaluating right now, looking at, will be this node. I will start looking at this node. Okay, so the data of this node not equal to null. Okay, and the contents of this node are lesser than a new item. Okay, if these two conditions are true, that means I have to move on. Before I move on, I will say that this node pointer is now my previous node. And to move on to the next this node, the node after this node, I will simply go to the next position referred to this node in the array, access the pointer field which is pointed to the next available node, and call that as this node. And I will keep on doing this until either one of these conditions is become false. So either I have reached my linked list, because of this condition will come first, I will move out the loop, or either I found a node which is no longer lesser than my new item. So either I reach, for M, I reach at the end of my list. For M, I reached my end of the list. That's why I exit the loop. Or if it's, say, for example, I'm trying to add K. For K, I don't have to move to the end, but I found a node of data which is no longer than my new item K. That's why I stop here, and I save it between this node and my previous node. So either one of these conditions, if either one of these conditions fail, i.e. I have not reached the end of my linked list, and I have not yet found a node which has data item which is larger than my new item, I will keep moving on forward. So as soon as this condition, one of these conditions fails, I will exit the loop. And once I exit the loop, I have really stopped at the position where this new node should be added. Now that position can be at the start, at the middle, at the end, depending on where I exited the loop. Okay, so again, one more time, as long as these two conditions are true, because this is a while loop requires the condition or conditions, in this case it's conditions, to both be true. As long as the while condition is true, then the loop will keep on going. As soon as one condition is false or the while condition becomes false, loop will end. The while condition will become false. Why? Because either one of these becomes false, because there's an and in it right here. There's an and right here. So and means both have to be true for this to be true. So if any one of this becomes false, then this whole condition will become false. Okay. So that's how this loop is operated. And inside the loop, if this condition is true, what that means is that I have not yet reached the end of my list. This means that I have not reached yet the end of the list. And the node that I'm looking at has a data item which is lesser than my new item. That means move ahead. Now, before moving ahead, I will say that this node that I just left will become my previous node. And my new this node will be told to me by this node itself. So the current node that I'm at right now is pointing towards the next node. So the next node actually comes from here. The current node I am at, the pointer value of the current node that I'm at will become my next node that I'm looking at. And this will keep on going, so on and so forth, until either I find a position where the data item is actually greater than my new item. Stop it there. Add this new node before that node. Or I have reached the end of my linked list. That means with the data item you're trying to add is the largest that is to be added yet, and it will become at the end. Now, as you can see, that I will exit the loop for either one of these reasons. Either I've reached the end, or I found a position which has data which is greater than my new data. Okay, so one thing we have to understand here is that basically if when I exit this loop, it is possible that I exit the loop with the intention of adding this new node at the start of my linked list. In which case, if I don't say, for example, have this line written here, I added this line afterwards. The reason this line is added afterwards because previous node pointer, the first instant of any assignment in previous node pointer we see is with inside this loop. So if I exit the loop with the intention of adding a node at the start of my linked list, that means that this loop will not run at all. Because if this loop runs, that means the loop body requires me to move on to the next node. And if the loop does not run, I will remain at the start and add this new node at the start. So this previous node pointer that we're talking about right now, this variable has no initialization in this algorithm before this point. So as you can see here, this condition is checking whether or not I'm adding a node at the start. And its comparison requires the value of previous node pointer and start pointer to be same. If that's the case, then that means I will add a node at the start. Now, this line that I just added right here, this basically assigns the contents of start pointer and basically copies the value of start pointer into previous node pointer. So if I do exit the loop, if I do exit of this condition becomes false and I do not even run the loop at all, and I come directly here, in which case this condition will be true here. Because yes, in fact, I did assign start pointer value to previous node pointer. And since the loop did not run, and because the loop did not run, it is time to add the node at the start of the list, this condition will be true. So I think this line should be added here. It makes more sense now because previous node pointer initialization has not been taking place. There is no initial assignment to previous node pointer. And the first time you see it here, and if I do a comparison without entering this loop, there is no record of the contents of previous node pointer before. And if I do that, if I compare previous node pointer with start pointer without ever entering this loop, it will create a confusion as to what are the contents of previous node pointer right now. So right at this point, if I am accessing this line without having entered the loop, at least I know what the contents of previous node pointer are. By the way, they are using PTR, so it should be PTR. Okay, previous node pointer. So moving on from there, now I've entered exit the loop. There's a possibility that I have to add the node at the start of my linked list. So this condition will be tested. If this condition is true, that means I'm adding a node at the start of the list. So it's quite simple. Simply what we'll do is we'll go to the array, go to the index position, which I'm calling new node pointer, and simply go to the pointer contents and copy the current start pointer contents to the pointer contents of this new node, so that this node will be pointing towards the existing start node. And this node has become at the very start. So let's just say I add a new node at the start of here. So what that should mean is that I am adding a new node here, right about here. This is my new node right here. So let's just say the contents of that node is A, because of which it should belong at the start. So what I do is that I will copy the existing contents of start pointer and copy them to the pointer position of this new node. So what that does is it links this node with this node. So now instead of the start pointer telling you this is the first node, this node is telling you that this node B is after me. This node B is after me, after A. In which case, the second step, I have to establish that in fact, this new node, let's just say that this is my new node. This is my new node pointer. My new node pointer is, I have to establish that this new node pointer is in fact at the start. So for that, I will copy the contents of new node to my start node, in which case the start pointer will be now pointing towards this new node, and this new node pointer will be pointing to the previously held start node. And this is how that's been taking place. So for that, in the algorithm, you're doing the exact same thing. So what we do is first, we will copy the contents of start pointer into the pointer position of this new node. And then I will update the existing start pointer to hold the contents of new node pointer. So now after this line has run, it will say that the new node that I just added is now the new start pointer. And the previous start pointer is coming after this new node. That is established by the fact that my start pointer is saved in the pointer position of this existing node. But if this is not the case, so that means I'm adding either the node in between somewhere, or I'm adding the node at the end. Now this else condition handles both situations. They handle both the end as well as between. So let's just say that I exited the loop because of my this pointer becoming null. Now my this node pointer becoming null means that I've reached the end of my list. So when I exit the loop because of that, I come out. My this node pointer is not equal to my start pointer, or my previous node pointer is not equal to my start. This condition fails. I come here. And what I do here is of course, when I came to the last node, regardless of moving to the last or in between somewhere, there's always an effort of maintaining the previous node. So what I do is, even if I'm trying to add a node at the end, this code will work for that. So what I do is that my new node that I'm trying to add, I will simply do what? I will copy the contents of my previous node pointer into my new node's pointer. So in this line, if I were to be adding a node at the end, so what this line would do is that my previous node pointer had null in it. Now that null is copied into my new node's pointer, because now this node will be at the end. So that null is basically being copied here. Now, and even if it's not the last node, and this is the node in somewhere between, let's say the previous node pointer is pointing towards node number 3. And what we do is we want to add a node between 3 and node number, say, 5. So what we do is, or 4 for that matter. So what we do is we copy the previous node. The previous node number 3 is pointing towards 4. I take that 4 and I save it on the pointer position of my new node. So my new node is now pointing towards 4 instead of my previous node pointing towards 4. And the previous node's pointer is saved having the new node pointer value. So let's just say, for example, I'm trying to add a node here. This is node number 1, 2, and 3. This is my node number 4 I'm trying to add. So by that condition, when I moved out of my loop, this was my previous node. This is my new node. This is my new node pointer has contents 4. My previous node pointer has contents 3. 1. And the pointer value of this node is 2. Okay. So what we do is we copy the contents of previous node pointer into the new node pointer's pointer position. So that 1 pointing towards 2, that 2 comes here. That node number 1 pointing towards 2, that 2 is copied here. So this new node is pointing towards 2. And this 4, this index position 4, which is my new node pointer, the exact pointer value is copied to my previous node's pointers index, the pointer field. So my previous node, which is node number 1, will point towards node number 4 like this. And my node number 4 will point towards node number 1. Now let's just say, for example, I'm trying to add a node at the end. Let's just say right here. In which case I exited the loop, and when I exit the loop, I exited the loop because this node has become null. Of course, since I established this node as null, this means that my previous node is this one right here. So let's just say node number 1, 2, and 3. This is my third node is my previous node. Same exact case. I will copy the contents of my previous node, which is null, into my new node, new node, which is also null. So this node is now pointing towards the last. And simply I will copy the value of this node or my new node into the pointer position of my previous node. So this node is node number 4. And I copied the null to the pointer position of node number 4. and I copied 4 into the pointer position of node number 3, like this. So either way, this else condition works for both states, adding a node in between somewhere and adding a node at the end. Whereas this condition works only for if we want to add a node at the absolute starts. Okay, so let's just say we want to delete a node from our linked list. So by logical diagram, what happens is that, let's just say I want to delete this node in between. So obviously there has to be some choice of what node I want to delete. So let's just say I want to delete the node with letter D in it. So first of all, I will start search for that node. Once I find that node, I will go to the previous node's contents, right? I will copy the previous node's contents. I will go to the previous node's pointer contents. I will take the node that I just found. I will copy the contents of its pointer, which point towards this, and I will overwrite them to my previous node's pointer position. So what that does is that the previous node, instead of pointing towards this node that I just deleted, will end up pointing towards the final node. So this is basically the transaction that's involved when deleting a node. And of course, I will have to take care about this node that I just discarded. I'll have to put this node back in my free list. So that's another step. So let's look at the algorithm. For delete node, I need to take as a parameter what data do you want to delete. So when I said I want to delete node number D, the data item that was input as a parameter was D. So first of all, I had to find the node that had contained the data value D. So I took as a parameter the data item that I'm trying to delete. Once that is input, I will start. Where do I start searching in my linked list? Obviously from the start. So like inserting into a node, I will also start from my very beginning. And the first node that I look at is my this node. And each node that I'm exploring for its contents, I'm exploring one node by one, each node one by one. So each node that I'm looking at the moment will be my this node. And my first this node will be told to me by the start pointer. Exact same procedure that we've used over here, exact same line. So, but the difference is that we were finding an insertion point for this in this algorithm, whereas in this algorithm, we're finding a node that holds this value, and we will start looking at the very beginning. So start looking at the very beginning, and the node that I'm looking at right now for its contents will be called this node pointer. Starting from the very beginning, if this node pointer is not equal to null pointer, obviously if the linked list has nothing in it, there's nothing to delete, obviously, and obviously start pointer will have null in it if there is no elements in the linked list, and that null will be progressed to this node pointer, and this condition will fail right away, and I will exit the loop. Same thing goes if I have reached the end of the list. At the end of the list, my last node will be pointing towards null, and when I move on from my last node to the next node, this node will also have null. Exact same method that was being used over here. So what's happening here? My condition, look at my condition. While this node pointer is not equal to null pointer, so I have not reached the end of my list yet. And the data at the index position of this node pointer in my array is not equal to the data item I'm trying to delete. So I have not reached the end of the list, and I have not yet found the data, not found the node that has this data item that I'm looking for. If none of these conditions are met, that means these both conditions are true. It's not equal to null and the data item is not found. If both conditions are true, my while loop is true. And if while loop is true, I will enter it. And when I enter the loop, basically what I'm doing is I'm moving ahead. So first step towards moving ahead is establishing that this node that I'm just going to leave will become my previous node. In which case, what I do is I will assign this node pointer to my previous node pointer. And next step comes moving ahead, in which what I will do is my current this node pointer is pointing towards the next available node, next used node. In which case, the pointer value of my current this node pointer will become my next this node pointer. Exact same technique that we just covered over here. Exact same, moving ahead, exact same technique, right? And I will keep on doing this until either I've reached and my linked list, or I have found the node that has this data item. And until that doesn't happen, I will keep on moving ahead. And this is how I keep moving ahead. First, keep record of previous node, then move on to the next node. Okay. Now I have exited the loop. So exited the loop means that either I've reached the end or I have found the position, either case. So if my this node pointer is not equal to null pointer, if my this node pointer is not equal to null pointer, that means that I did not reach the end of the list. If I reached the end of the linked list, that means the node that I was looking for, I didn't find it. I'm looking for node number. I'm looking for the node that has data item M in it. Now, is this M? Is this node have M? No. Previous, this. This node have M? No. Previous, this. This node have M? No. Previous, this is null. Exit the loop. Now, is my this node pointer equal to null? Yes. That means the item I'm looking for is not in this list. But if my this node pointer is not equal to null, that means I stopped at a place where the node actually had the data I'm looking for. So let's just say I'm looking for D. D is here. I start at my start. This is my start pointer. This is my start node. This becomes my this node. Is it D? No, it is not. Previous, this. Is this D? Yes, stop here. So this node pointer, say index position 2, is not equal to null. And if it's not equal to null, so that means I exited loop with the actual position where that data item is, where that data item is, which I want to delete. So that's where this condition is used here. If this node pointer is not equal to null pointer, it means the position that you're trying to, the data item that you're trying to access exists. So if this is true, that means there is something to delete. In which case, if this node pointer, the second condition, sub-condition, nested if condition is that if this node pointer is a start pointer. Now, what that means is that, say I'm trying to find B, I'm trying to delete B. If I'm trying to delete B. So this is my start pointer. And this is also the node that I'm trying to look for. So basically, this node pointer, when I exit the loop, will also be my start pointer. So if this node pointer is equal to start pointer, it means the node I'm trying to delete is the first node. So if this condition is true, the first node is to be deleted. So if this node pointer is equal to start pointer, what I do is that existing start pointer's pointer, existing start node's pointer position value will be assigned as the new site pointer value. So let's just say that B node was to be deleted. B node is in pointer position value 1. Start pointer has 1 in it, pointing towards this node. This has 2 in it, pointing towards this node. Now, since I want to delete this node, 2 will be saved in my start pointer value. Now, start pointer will be pointing towards this new node, this one right here. So what happened here is my existing start node, the pointer value of my existing start node will be copied to my new start pointer. And my start pointer is now pointing towards this node as opposed to this node. So that's what happened here. If my node is the first node that I want to delete, in that case, I will do what? My existing start node that was previously start node is pointing towards the second node. Now this second node will become my new start, the new first node. That's why that pointer position value will end up here. But if this condition is not true, that means the node that I'm trying to delete is somewhere in between or possibly at the end, whatever it is. So you will delete it accordingly. So what's happening here is that I will take, if it's in between or even somewhere, so I will have a record of my previous node. So in that case, what I will do is that, again, there's a mistake here. This is list previous node dot pointer will be assigned with this node dot pointer. Now think about this. I am deleting this node. This is my previous node. I will delete this node. So basically I want this node to directly point towards this node. In which case, What I will do is that I will copy this node's pointer value into previous node's pointer value. So again, this line should be, there's a mistake here. It should be mentioned like this. This line should be mentioned like this, that list previous node pointer dot pointer. Pointer is assigned with list this node pointer dot pointer. So basically they're just missing the dot pointer part over here. This line should be written in this way. They have mistakenly not written the dot pointer part over here. Other than that, it's fine. Okay, so this is what we're doing here. Again, I'll repeat it, that if I just deleted this node, so what I want to do is that I will take the current this node pointer's pointer value, the pointer field. I will assign that to my previous node's pointer field. So if this was node number 3, this was node number 2, this was node number 1, this 2 is pointing towards node 3. I copied that 3, this 3 here. I will copy that 3 to the pointer position here. So that's why node number 1 will point directly towards node number 3. And this node has been ignored from the whole situation, right? So that was missing over here. Now, after I have deleted either case from the start or in between or in the end even, okay, even at the end, this code works even for the end. How does that work for the end? Obviously, if my previous node is existingly currently the last node, so in that case, simply copying pointers means that I'm copying the existing null into this previous node null. So basically, if I'm deleting the last node over here, say for example here, now this is my previous node, this is my this node I want to delete L. So basically that means that I'm copying the null into my previous node's pointer position. So the same code can work for either transferring null values or non-null values, either way. So this else condition works for both situations, deleting from in between or deleting the last node. It works for both ways. This works only for the first part, okay? But this is where the important part is. Now imagine that I just deleted a pointer. I just deleted a node. So this deleted node is now free. This free node has now yet to come in my free list. So what we do here is that we will take this node, this node that I just deleted, and I will assign the current free list pointer to the pointer position of this node that I just let go. And I will update my free list pointer to the pointer position of this node. So basically what that means is that, imagine this is my linked list right here. Say this is my stack of nodes that are free, they're not used. So let's just say this is node number 4, this is 5, this is 6, 7, and 8, right? And my free list pointer is pointing towards 4 currently as the next available node, obviously. So let's just say that the node that I just deleted, this node, let's just say that this node that I just deleted is actually node number 2. It's node number 2. Node number 2 contains the data that I wanted deleted. So this node is actually node number 2. So what I do here is that, let's just say, imagine that this is the node that I just deleted. This is my node number 2. This is my node number 2, this node. Okay, I just deleted this node. So what I want to do is that I want to link this node back to my free list. I want to link this node back to my free list. So what I can do is, if I have a pointer value here, something that was previously used in my existing linked list, what I do here is that I will simply copy my current free list pointer value, which is 4, into the contents of this node that I just deleted. So this 4 comes here. Now what that does is that this node will point towards this node as the next available node. And basically you have linked this free node to my existing free list. At the same time, if this is node number 2, I update my free list pointer to say that now node number 2 is my next available node. So it's like I have a stack of free nodes and this node is just let go, it's just free. So simply what I do is I put this node at the top of my existing stack of nodes. And how am I establishing order? Through pointers. So my next available free node was 4, pointed by the free list pointer. I took that value, I copied it to my pointer position in my newly freed node, so that this newly freed node is pointing towards this node number 4. And this newly freed node is actually 2. So what I take that 2 is, and I copy it in the free list pointer to tell everyone, to tell the algorithm, the next available node that you want to use ever is node number 2. And this would have worked even if there was no there were no nodes in my free list. So how would have worked? How would have worked in that case? Well, in that case, my free list pointer would have null in it, right? So in that case, I will simply copy the null here, and this would be my first and obviously most bottom node in my stack of nodes. But still, it will work. The algorithm will work. So this is how I am updating. This is how I am updating my node, my free list. I'm adding this newly freed node back to my free list. Now you must be wondering that what happened to the data of this node? This data had something in it. This data had something in it, and I wanted to delete this data. Technically, I just removed this node from my existing linked list back to the free list, but that data is still there. I didn't do anything about it. That's okay, because next time when I use this node to add data, as you remember inserting a new node in my linked list, what you do is we instantly write the new item in the data position of this new node. And automatically when I use this node again, this position will be overwritten with updated data. So you don't necessarily have to delete it here. Every time you use this node, this position will be overwritten with a new data item. So it works either way. Okay, last two features of our linked list algorithms include finding a node and possibly outputting all data of all nodes, right? So let's look at the sequence of finding a node first, okay? So finding a node, obviously I need the value that I'm looking for in my linked list. So as you can see here, we will be taking that value, that data item A, B, C, whatever that data item is, as a parameter. This, unlike the other subroutines, this is actually a function. So what that means is that it will be returning some value, okay? And it's returning an integer type value. So basically the value it's expected to return is the pointer position, the index position of wherever that data is that you're looking for. And if, for example, that data item is not found, this function will be returning a value null. It's understood. So anyway, obviously, like in all algorithms for inserting, deleting, whenever you're trying to search for something in a linked list, the best place to start is at the very beginning. And the very beginning is identified by the start pointer. So we've changed the names a bit. So the node that I'm exploring at the moment to see whether or not it holds this value will be from now on referred to as current node pointer. So my current node pointer will be my start pointer. So that's why the contents of start pointer are copied into the current node pointer. So I start at my current node pointer. as long as my current node pointer is not equal to null, because if my current node pointer becomes null, that means the linked list has reached its end. Okay, so as long as this is not true, as long as this is true, that current node pointer is not null, and the current node pointer's data is not equal to that item I'm searching for. If both of these conditions are true, that I have not reached the end, and I've not found the data item that I'm looking for, I will keep on moving ahead. Now again, how do I move ahead? As in the previous cases, we're keeping record of previous nodes. Since I'm not making any changes, I'm simply returning whether or not, I'm simply highlighting whether or not a particular data item is here. So in that case, since I'm not making any changes to my linked list, I don't have to keep a record of my previous node in this algorithm. So in simple terms, if I did not find the node where that data item is, I just keep on moving ahead. So in this case, if you can see here, I did not find the data item I'm looking for, in which case I will simply move ahead. So what I do is, from moving ahead from current node is very easy. The pointer of that current node is simply telling me how to move ahead. So the next current pointer will be pointed out by the current pointer position of the current node. So if I'm at the current point right now, so node number 1, the pointer value of node number 1 is 2. So the next iteration, my current node will become 2. If I'm at the last node, if I'm at the last node and my last current node, the pointer position will be null, in which case that null will be copied here. And then when this condition is checked, it will fail and I will exit the loop. I've reached the end of the list. In any case, either I will reach the end of the list, or I've reached the position where the data item has been found. Now, when I exit the loop, I will exit the loop with current node pointers 2 possibilities. Either the current node pointer will have null in it because I reached the end of the list, or it will have a non-null value, in which case I exit the loop because I found the node that I was looking for. And simply when I exit the loop, I will return the value of current node pointer. And if the function returns null, that means that value was not found. And if it returns a non-null value, it means that that index position is found where that data was stored. Simple as that. In the last aspect, I am not doing any comparisons. I am simply moving from my start node all the way to the end node, and turn by turn outputting all the contents of each and every node. So again, this is a procedure. And since I'm not searching for any node, any particular node, I am not categorizing in, I'm simply outputting all nodes. I don't need any parameters whatsoever. I will simply start at the beginning, take the contents of that node, output them, move on to the next node until I reach the end of my linked list. So as always, there is no parameter required here. And also this is a procedure. Unlike this one, it's not a function. I'm not returning anything. As always, the best position to start is at the start. So the start pointer is telling me that this node is my current start node. I copy the contents of that to my current node pointer. If my current node pointer is not equal to null, so that means I've not yet reached the end of the linked list. Simply what I will do is I will output the data field of my current node, and then I will move on to the next node. How do I move on to the next node? As by now, you must know this very well, that the current node's pointer position points to the next current node. And you keep on doing this until your current node becomes null. So let's just say I'm at the last node right now. I will output the contents of the last node. And when I move on to the next node, my current last node's pointer position has null in it. I will copy that null here. And when the condition is tested again, it will fail and I will exit the loop. So, and that's about it for all outputting all nodes in this linked list.